Okay. Hello. Good morning, students. Am I audible? Just confirm
Yes,
whether
sir.
I'm audible or not.
Yes, sir.
Yes. Yes.
Yes, sir.
Clear?
You're audible.
Okay then. So let me start today's class where we left in the last. In last week, I took only one class, right? So we had on Tuesday we had a holiday. So mm, in the last class we have derived isentropic relations, right? So um, we took a supersonic field like this. Okay. So if there is no disturbance in between. So what are the how uh, the variables T1 and T2 are pressure or any density change at two different locations, how they are related, okay, with respect to high speed flows. So that for this assumption, we took that the flow is isentropic, right? So first we derived the isentropic relation. No, first we derived the relation for entropy, right? S2 minus S1. And then from that, we assume that since the entropy is going to be constant, that means Cs is equal to 0. From that, we have derived how parameters at two different locations in a supersonic field without any disturbance. Even though there may be no disturbance, uh, the variables will be related with each other in some way. So here, the specific heat is governing that. So that is what we found out. So we have done this relation. Now, as we know, this is high-speed learning subject, right? So we will be dealing mostly with high-speed flows. So we'll be. Well, let me take a new whiteboard first. Yeah. So since we are going to deal mostly with high-speed flows, yeah, we'll be dealing more with supersonic speeds, right? Supersonic or any hypersonic speeds. Okay, so here, as I said in the beginning, in the introductory class of, you will be predicting what is the, let's say the aircraft is moving in this direction. That means the flow field will be at some m infinity equal to 3. Okay, so what is the velocity here? Let's say this is m1 instead of m infinity. Let me call this as m1. Okay, so you should be able to predict what is m2 there. Okay, so because of this accumulation of air molecules there, so whenever you have some certain molecules, air molecules there, whenever the new molecule is colliding with this, then after that, let's say this m1 was at 3, then after that, when it is colliding with this buffer region or a shock region, we call this a shock. Okay, where you have a lot of air molecules accumulated. That means density will be higher here. Okay, so once the air molecules are colliding with this, before passing here, it will lose some momentum, right? Because it is colliding with these particles, right? So that is why you will see that M2 will be different. Okay, how it is going to be different, whether it is going to decrease or increase, and all will have to predict them, right? And also, if say M1 is changing, then that means P1 is also something here, and P2 will be something here. T1 will be something here, T2 will be dropping, right? Again, if there is another shock there, that means here again it will be M3, P3, T3. So whenever the air molecules are passing through each and every shock, then there will be changes in variables. So those things and all we'll have to predict it. So that is what is the target aim of this particular subject, right? And after that, any hyper supersonic flows, let's say even if you take any nozzle or anything, we'll have to predict what is the, if say you have a nozzle like this, what is the pressure here, and based on this pressure, what is the Mach number that we are going to get at the exit. Okay, so let's assume that this is nozzle exit. Okay, NE. So certain nozzle exit, what are the parameters and all. So those things and all, we will have to predict them, right? So that is what is our target. I keep repeating this at every instant of this course because you should know why we are studying something. Okay, so today what we will do is, as I said, we have to predict something what is going on with M1 and M2, right? So in order to do that, obviously this is a fluid flow, right? So this is the fluid flow. That means we have to bring in the governing equations, right? So whatever in the previous aerodynamic course that you learned, um, you might have derived the Navier-Stokes equations and all. In the fundamentals of aerodynamic course, you have already derived all the um, governing equations, right? And so in that, so those Navier-Stokes equation you would have already done it for three-dimensional fluid element. You might have taken some fluid element like this, and what on each fluid element, what is the stresses that are acting? Using those things, you might have evaluated for the entire three-dimensional one. But since here in this high-speed aerodynamics, as I said, we need very simple empirical relations, right? So we'll have to derive something, a simple equation, so that if say something is m1, and based on the, let's say you have some wedge like this instead of aircraft. So this is an aircraft shock wave around an aircraft. I take a wedge, simple wedge, and you have some m infinity equal to 3. Okay, so this wedge obviously it will have some certain angle, right, theta. So for that angle, since you have this flow moving at very high supersonic speeds, you will generate some shock wave, right? So which will be of some beta, right? So here with the if m1 is 3, then m2 should be something, right? And p1 is something, then P2 also should be something, right? So that means this flow already, obviously this is a flow field. So we have to derive some empirical relation which should be as simple as possible, so that using a simple equation you should be able to bring some m2 as a function of m1. Okay, you need to bring some relation, and at the same time P2 also you can bring it as a function of m1. Okay, you will see that m1 becomes a major criteria where you can predict everything. T2 also you can predict it as a function of m1. Okay, so all these things you will be able to predict them. So that is why what we'll do is you have derived all the continuity, momentum, and energy equations. Those are the governing equations, right? So for any fluid flows, that is what is the equations that govern the flow, right? So here, what we'll do is we'll simplify those equations in such a way that we will take one-dimensional effect only, because this is a supersonic flows. We'll first assume that this is a one-dimensional flow, and with that we'll try to bring in some relations, so that we'll get the governing equation. From that we'll be able to calculate all these. Okay. So in today's class, what we'll do is we'll take all the continuity, momentum, and energy that you derived in integral form, right? You might have learnt it in the form of integral, or you might have converted that to differential also. Okay. So both of them you might have learnt it in integral form, how it is going to be; in differential form, how the governing equations are. So what we'll do today is we'll take the governing equations in the integral form. We'll simplify it in one-dimensional form such that you will get direct relation between what is P2, or what is the difference, what is the relation with P1 or P2 or U1 or U2, anything like that. Okay. So why we do separately here is, in the last class, whatever relations that you derived, uh, here you have derived it in terms of only P1 and P2. So here if you see in the last class, whatever we derived, I'll directly go to the result. Yeah. So this was the result that we showed in the last class. P2, if say you have supersonic field, P2 by P1 or rho 2 by rho 1 or T2 by T1, how they are related with one another, right? So here, if you see, there is nothing that is relating the velocity of the flow field, right? So we did not include anything with u. Okay. So since this is a high-speed flow, obviously we'll be dealing with velocities, right? So now we'll see that after we derive this relation, everything will be in the function of u. Okay. So today what we'll do is we'll derive the governing equations. Okay, one-dimensional flow equations. Okay. So the topic will be one-dimensional flow governing equations. So let me first start with the flow field, how it is. So let's take a control volume like this. Let's take a control volume. Okay. So here the flow is flowing in this direction. Okay, let me put some arrows there. The same thing on the other side. Obviously, based on continuity equation, whatever is flowing inside should move out, right? Okay. So only thing is that let's assume that we have some disturbance here. Okay. I'll take a region like this. Let me make a rectangle. Okay. So I have a region like this. I'll mark this region. Okay. Assume that there is a shock wave or anything. We are disturbing the flow. Okay. It can be a shock wave. Can be a shock wave, or it can be some, you are adding some heat. Okay. Heat addition. Anything like this. Okay. So what I'm trying to say is we are disturbing the flow inside. So whenever you have the incoming flow with U1, let's assume that the flow properties at this point. Let's take this as region 1 and region 2. Okay. So this will be the incoming velocity. So the internal energy was E1, pressure was P1, temperature was T1, density was rho1. Same thing. Once it is undergoing some disturbance, right? So we assume that this is some disturbance region. So after that, once the flow is moving, uh, passing the disturbed region, then obviously all the parameters will change, right? So we'll have U2, we'll have E2, we'll have P2, the T2, and rho2. Okay. So I'll delete this. It's not needed. Okay. So assume that this is some disturbance. Okay. Will not write it as a disturbance. So this is some disturbance. So this entire region is okay. This is a rectangular control volume. So we'll take a control volume. This is a uh, rectangular control volume. Okay. So this is the flow field. Okay. Now what we'll do is we'll start bringing one by one. So now we'll start with continuity. Okay. So continuity equation. We'll try to bring one-dimensional form of continuity equation. Yeah. So obviously, first thing that you need is you have to recall your continuity equation in integral form. Okay. So let's start with that. So continuity equation in integral form. Okay. So this you may have already learned it in integral form. In fundamentals of aerodynamics course, you already know that. So time rate of change of rate of change of mass flow will be equal to time rate of change of decrease in work and mass flow, right? So first thing that we will write is amount of mass flow in a control volume. What is the mass inside this control volume, right? So that will be surface integral rho v ds, right? Rho v ds, rho v dot d, and rate of change of mass inside the control volume. Obviously, it will be decreasing, right? So that is why we'll have a negative symbol, right? So volume integral, oh, rate of change, right? I forgot. We will have minus, then dou by dou t, volume integral rho dv. Okay. So this minus symbol because the mass is decreasing, right? If you take control volume at that particular instant time, the mass will be reducing. So that is why we take negative symbol. Okay. Now the assumption, the first assumption that we take here is when you are doing this simplified equation, first assumption is the flow is steady, okay, steady flow. Second thing is no body forces, okay, no body forces, right? So that means steady flow means dou by dou t is equal to 0. Okay, so for steady and for steady flow, here we don't have any body forces, right? For steady flow, dou by dou t is equal to 0, right? So that means the surface integral rho v ds is equal to 0, right? Now what you will do is, as I said here, we need to split this for the integral for the entire control surface, right? So this entire control surface, this is what is the this is what is now we have, right, for steady flow. So this term has gone to 0, right? So this term has gone to 0. Now we have to integrate it at the same time. This capital V is, as you know, this capital V. This capital V is Ui plus Vj plus Wk, right? So we'll assume that the flow is one-dimensional, right? So that is what this equation is. The flow is one-dimensional. I'll write here 1D flow. Okay. So that is what is our target, right? We are trying to bring one-dimensional form of grounding equation. That means only U will be there. The other parameters will not be there. So here, if you see, obviously this particular this region will have an area, right? So this region will have area A1, and this region will have area A2, right? Okay. So here ds is the surface area, right? Okay. So now you can write rho u1 into A. So here, when you have learned this continuity and energy equations, all these equations, obviously you might have learned that if you take a control volume like this and you take a control surface like this, obviously ds will also have a direction, right? And velocity will also have one direction, right? So ds also will have some direction. So here for rho 1 and u1 at this surface, in region 1, if you take a1 and u1, a1 and u1, both of them are in opposite direction, right? So the ds will be pointing in the opposite direction, right? So, the ds will be in opposite direction. The surface, let's take a cubical element like this. This sign convention is very important. Okay, so this area, this particular area, will have its direction in ds. Okay, this particular will have in this direction. Okay, so this will have in this direction ds, and this will have the direction in this ds. Okay, if say u is there here, then the product of u and ds since it is in opposite direction and u it is in this direction, then obviously it should be a negative symbol should be there, right? Because a1 is in opposite direction. Okay, so you have to be careful here. Okay, area is also, the face area is very important here. In which direction the face is pointing. Okay, so that is why this vector calculus, each and every small intricate things are important. Okay, now you have, now if you see on the region 2 here, in the region 2, A2 and U2, both of them are in the same direction, right? Because the face area here, this face area is this one and U2, both of them are in the same direction. Whereas here, A2 and U2 are pointing in the opposite direction. Okay. A1 and, sorry, A1 and A1. Okay. Okay. So now here, rho 1 U1 A1 plus rho 2 U2 A2. This plus here is, as I said, here on the both U2 and A2, both of them are in the same direction. The vector is in the same direction, whereas here they are in opposite direction. Okay. Now this is equal to 0. Now here, as I said, in this control volume, the area A1 and A2, both of them are same, right? Because I am not taking any different control volume, right? So it is a rectangular control volume. Opposite phases is going to be the same. So that means A1 is equal to A2. Okay. So since the control volume is a rectangle, A1 is equal to A2. Implies now you get the relation rho1 U1 is equal to rho2 U2. Okay. So this is one-dimensional form of continuity equation for a high-speed flow where we are assuming no body forces and we are assuming the flow is steady. Okay. So this is continuity equation. Now we'll look at momentum equation. These things are foundation. Okay. So using these relations only, we'll be getting all the relations for speed of sound or the Mach number relations that I told you, right? You will be, if say you have a wedge like this, you have theta. So you can predict what is the angle of this shock wave, beta, based on the incoming Mach number. All these relations you can predict them on paper itself. Okay, so those things further, these are the equations that will give us foundation. You will be seeing how we are going to use in the further classes. Okay, so first we'll get our governing equations first. Okay, so now continuity has come out. Now we'll go to momentum equation. Now we'll get into momentum equation. So obviously the momentum equation came out from Newton's second law of motion, right? F equal to ma. So F is equal to m. A can be written as dv by dt, right? So velocity, change in velocity by time. So that means F is equal to d by dt of mv. Okay, right? So this is mv is the term momentum, right? mv is momentum. So I'm just giving the quick brush up for you, okay? Not teaching the derivation of the momentum right now. So based on this only we derived our momentum equation, right? So here in the right hand direction, in the LHS, you dropped all the body forces, right? Pressure, based on the pressure, how much is the force or friction forces, all the terms will be coming in this. Whereas on this in this side you will be giving the momentum terms, right? So now what I will do is we'll directly consider the integral form of momentum equation is the integral form of momentum equation. Okay. So the first I'll mark this as one. Okay, so this is very important. Okay, now this was continuity, right? Now we'll go to momentum. So in momentum, the integral form, obviously the first thing that we'll start writing for this. Okay, so d by dt of mv. Now for that, if you see momentum inside the control volume, let's say this is our control volume. Okay, let's say it was three-dimensional because you learned for three-dimensional, right? Let's take a three-dimensional control volume like this. Yeah. So whatever flow is going inside, we'll try to move outside, right? So what is the momentum already inside? So rate of change of momentum. Okay. So that will be mv, rho v ds. M is rho v ds, right? M is rho v ds, and again v should be there, right? Okay. So now this is v. So this is surface integral for the entire all the three x-axes. So this is what is momentum. Now this should be added with the change in momentum inside. So because of some fluctuations inside this control volume, okay, because of that there will be some changes in the momentum, right? So that should be with time integral, with the time rate of change. So that will be dou by dou t. So that will be volume integral v rho v d. Okay. So this is m and this is volume. Okay. So this is time rate of change. Now in the other direction, here you have F, right? So this F here, obviously there are multiple types of forces acting, right? So one will be the body force and the other one will be pressure force, right? Because of pressure, you will be seeing some uh, force being acting on this fluid element, right? Because on all the direction you will have force, right? So same thing I will say here. Obviously for this surface area, take this as surface area. Okay, so for this the vector ds will be in the opposite direction, right? Same thing for this. Pressure and ds, P and ds are in opposite direction, right? Can you see that? So that means the product of PDS, if you take the surface integral of PDS, obviously all the vectors are in opposite direction. That means you should have negative, right? So this vector in vector calculus, this point, the signs are very important. Okay, you should be careful with that. Now this is PDS. Now obviously the other one is body forces. Body forces that you can take as volume integral rho F T. Okay, F is body. Now when I started this, I told you that we are assuming that the flow is steady and for steady flow with no body forces, obviously, can you take this term as 0 since F is equal to 0? Okay, right? F is equal to 0 and dou T also is equal to 0. So that means this term will go on, right? So now you will be ending up with only two values there, right? So that will be, let me take as implies surface integral rho v dot ds. So this is mass term and then velocity mv. So this product is mv, right? Is equal to surface integral p d. Okay. Now here this vector, as I said here earlier, v is uy plus vj plus wk. Okay. So now since the flow is one dimensional, for 1D you will have v is equal to u only, right? Okay. For 1D. So that means, can I write? So taking surface integral, you are adding on all cases. So let me bring this figure again. I'll paste it here. Because I'm taking this. Let me put it here. So for this PDS, now can I take? I have to take integral on both this area, both the surfaces, right? So for the entire control volume, I have to take them. Now what I'll do is, can I write rho 1? Can we write rho 1 u1 into a1 into u1? There is another u, right? Plus, obviously on the other side also we have to add it, right? Rho 2 u2 a2 into u2 is equal to minus. So this P and A, both of them are in opposite direction, right? So that means P1 A1 and P2 A2. So again we will have minus P2 A2, right? No, something is here. Pressure and A1. Yeah, P2 is in the opposite direction, right? So this will be P2 A2 will be positive. Okay. Yeah, here I have think I made another mistake here. This should be minus, right? Because U2 and A2, no, this one. U1 and A1 are in opposite direction. So you have to take negative here. Okay, now implies A1 and A2 are equal, right? A1 is equal to A2. Let me write, since A1 is equal to A2. Since A1 is equal to A2, all the area will move, right? So now you'll end up ending up with rho 1 U1 square plus rho 2 U2 square is equal to P1 A1 minus P2, sorry, P1 minus P2. Since A1 is equal to A2, everywhere area will move out, right? So now P1, so finally you will get P1 plus rho 1 U1 square is equal to P2 plus rho 2 U2 square. Okay, so this is one-dimensional form of momentum equation. Okay, you'll be seeing how these equations will be useful when we are trying to derive all the Mach number relation. Okay. So this is a one-dimensional form of momentum equation. 1D form of momentum equation. Up to here, anyone have any issues? Please ask me now itself. Based how I'm taking this now. Okay, how these signatures are in the opposite negative, positive, why I'm taking, I think you are understanding it, right? So the area will have some vector. Okay, so area also will have some vector. Okay, so that will define in which direction the flow is moving. Okay, so that is why you'll have to take. Okay, then let's if this is the surface, so for this ds will be in opposite direction, whereas pressure will be in the other direction. Okay, same thing on this. Okay, so that is why you'll have to be careful when you are assigning some signs there. Okay. So this is momentum equation. Now we'll go to energy equation. All these things we'll keep them. Okay. Even in if you think about in terms of your examination, there will be this subject will deal with lot of mathematics. Okay, so a lot of the derivations are there. If you are writing only these three equations, the final results, momentum, 1D momentum, 1D energy, 1D continuity. So all these three will have certain weightage. Okay, at least you will get some 4 or 5 marks like that. Okay. So even in exam point of view, this is because for every derivation that is there, this is the foundation. So you'll start with this continuity, this momentum, and energy equation. Okay. So that is why if you are writing only those three, you will get some marks. Okay. So now we'll go to energy equation. Every derivation in this course will be based on these one-dimensional forms. Okay, so that is why everything throughout this entire course you will be writing this equation, these three equations repeatedly. Okay. Now we'll go to energy equation. Energy equation, as we know, from where we got. So energy equation was derived using second law of thermodynamics, right? Second law of thermodynamics. From second law of thermodynamics, you brought that, right? So where change in internal energy is equal to the amount of heat added or removed with respect to heat done or work done or work done upon the system, right? So that is what is second law of thermodynamics. Delta E is equal to delta Q plus delta W. Okay. So whenever there is some work done on the system, obviously there will be some heat added or removed from the system, and at the same time you will have some internal energy change. So that is based on this. So if you take these three terms, B1 plus B2 is equal to B3. So each of them we try to bring it for fluid flow, right? So where what is B1 there? Rate of heat added. Okay, so I'll just brush this up. Okay, rate of heat added, rate of heat addition. So and B2 is a rate of work done on fluid. Okay, rate of work done. Okay, then again B3 is rate of change in internal energy. Right, this is the foundation through which you derive the energy equation, right? So directly I'll write the integral form of energy equation is, so how did I write? Obviously these three terms are needed. Rate of heat addition. So that heat addition you wrote it in terms of surface integral Q dot. So rate of heat addition Q dot, then rho dV. Then again we had rate of work done. Work done can be done based on two systems, right? One is PdV work, right? Because of pressure, you will have some work done. So same thing, PV, right? PV work done. So surface integral P V dot ds. Okay. So V here is volume, not velocity. Okay. Now plus again, there will be some body forces, right? So the body forces obviously should be volume integral F dot V into ds. Okay, so that will be equal to rate of change of internal energy. Internal energy, if say you take a fluid element, what is the already existing internal energy inside, and at the same time, what is the rate of change of internal energy because of some fluctuation. Okay, because suddenly something happens, because of that you will see that there is some change in. So that rate of change also you have to bring in. At the same time, you should bring in the already existing internal energy inside. Okay. So that means if say we are looking at two terms. So one is surface integral rho into E plus V square by 2. So this is kinetic energy since the only E you can write it for fluid element, but since the fluid is moving, then obviously it will have some kinetic energy, right? So that is why we have to write rho V square by 2. Okay. So that is after that rho V square by 2 by VDS. Then again you will have another term which is time rate of change, right? So time rate of change, dou by dou t, it will be volume integral rho into E plus V square by 2. Same thing, we are taking the time rate of change. Okay, so this will be dV. Okay, time rate of change. Now if you see here, so let's take this entire term as Q dot. Okay, so here this term, the first term, we'll take it as Q dot. That will be heat rate of change of heat. Then that will be minus. As I said, the steady flow and body forces, no body forces, right? Since you will have no body forces, this will be 0, and time rate of change, this for steady, this will be 0. Okay, so let me write for steady flow with no body forces plus Q dot minus surface integral, this PVDS is there, right? So work done based on pressure, PVDS is equal to surface integral rho into E plus V square by 2 V dot d. Okay, only these two terms. Sorry, three. Now say same thing, evaluating. Let me bring again the diagram that we have drawn. So we have to take surface integrals, right? So the one dimensional, so yeah. Now we are evaluating the surface integral over left and right surface. Surface integral over left and right hand, right surfaces for 1D fluid. Okay. So for that, now if you say Q dot minus, so obviously here P1, U1, P1, U1, and A1. U1 and A1, both of them are in opposite direction. That is why you have to take minus there. Okay. Which will be added to P2, U2, and A2. Okay. And that will be equal to minus rho 1. So this term, rho 1, E1 plus U1 square by 2 into U1, A1. Right? This minus obviously for this phase, right? U1 and A1 opposite direction. So that is why you have to take minus this. And now plus for the other phase, rho 2, E2 plus U2 square by 2 into U2 A2. Okay. So now this can be simplified and written as Q1. Since the area is going to be the same, obviously A1 you can assume A1 is equal to A2 is equal to A. So I'll write it as A because here I cannot remove it because Q dot will have no A, right? So that is why Q dot by A, if I want to remove it, so this will be in this form, right? Or substitute the entire equation with the A. Now that becomes Q dot minus A will plus P1 U1 A1 minus P2 U2 A2 is equal to minus rho 1 into E1 plus U1 square by 2 into U1 plus rho 2 into U2 plus U2 square by 2 into U2. Now again, let's bring all the one side terms. Okay, so Q1 by A plus P1 U1 A1 plus rho 1 into E1 plus U1 square by 2 into U1 is equal to P2 U2. A1 is not equal to. Let me tell you this. Remove this A should not be there. Plus rho 2 into E2 plus U2 square by 2 into A2. Now if I bring rho 1 and u1 on the numerator, that will be q1 by rho 1 u1 a1. Sorry, a. Can write it as a only. Plus rho 1 by u1 by rho 1 u1 plus e1 plus u1 square by 2 is equal to, if I take rho 2 u2, I have divided it, right? That means here also I have to do that. u2 rho 2 u2 plus u2 plus u2 square by 2. So this will be divided by rho 1 u1. Okay. Now from continuity we know that from continuity rho 1 u1 is equal to rho 2 u2, right? So this was from continuity or from one from continuity equation. So that is what was our finding, right? So that means these two can be cancelled out. So now we'll end up with here u2 and u2 will go up, u1 and u1 will go up. Now I'll write this q dot by rho u as heater. Okay. So can I write? Apart from that, we have from enthalpy definition of enthalpy. Let me bring in the definition of enthalpy from definition of enthalpy. So change in enthalpy is equal to internal energy plus work done, right? So P plus PV. So I'll bring that here. In terms of in the place of E1 there, I'll bring in these two. Okay. Now because of that, obviously this term is Q, first term. So Q plus P1 by rho 1. Can I write it as P1 by rho 1 here? You see this P1 by rho 1 is P1 V1, right? Plus E1 plus U1 square by 2 is equal to P2 by rho 2 is also P2. Rho 2 rho 2 is the reciprocal of volume, right? So that is what I'm writing. P2 V2. This is volume V2, not velocity V2. Okay. So plus E2 plus U2 square by 2. Now can I write P1 plus P1 V1 plus E1 as H1? I'll write this as H1, right? Enthalpy from definition of enthalpy. So H1 plus U1 square by 2 is equal to H2 plus U2 square by 2. Okay. So I'll rewrite again. I'll rewrite again. H1 plus U1 square by 2 plus amount of heat added is equal to H2 plus U2 square by 2. This is what is energy equation. Energy equation for 1D flow. Energy equation for 1D flow. So what this says is whenever there is any free stream flow and if there is some heat added, so this is what is the change in parameters on the other side. Okay, enthalpy will be changing to H2 and U2 velocity will be changing to U2. So with these three equations, we will be getting all the fundamental empirical formulas in terms of Mach number or whatever we are going to derive in high-speed aerodynamics are based on these three equations. Okay, so we'll see how we'll be using this. Okay, the simple derivations, these results of these derivations, you'll be using those three equations repeatedly. Okay, so summarizing it. So summarizing. summarizing 1D flow equations. So we derived 3 equations, right? One is continuity, where you'll calculate rho1 un is equal to rho2 u2. The other one, energy momentum equation. P1 plus rho1 u1 square is equal to P2 plus rho2 u2 square. And finally, the energy equation, H1 plus u1 square by 2 plus q is equal to H2 plus u2 square by 2. Okay, all the 3 equations we'll be using it repeatedly and repeatedly for each and every derivation in this entire course. Okay, so with this we'll be getting all our simple empirical solutions. Okay. Any doubts up to here? So with this we'll conclude our today's class. Okay. So this is the foundation. We'll start deriving one by one. Okay. Next, and before that, I'll teach you what is the different flow Mach numbers, flow regimes that are there, and after that we'll proceed to all the derivations. Okay. So any doubts up to here?
No, sir.
Okay.
Yes, sir.
Wait for. So, yeah, and then, okay. Okay. So that will conclude today's class. Tomorrow we'll see speed of sound and different flow regimes that are there. Or we'll discuss what is the difference in supersonic flow, hypersonic flow, transonic flow, subsonic flow. What are they and what is the complexity in those flow fields? Okay. So one by one we'll discuss. Okay. Okay. Any if there are no doubts, then I can end the session for today. Yeah.
No doubt,
Right?
sir.
Okay. Goodbye.